Okay, so let's move to second part is fluid-fluid chemical reaction. So as we mentioned, fluid-fluid chemical reaction can be a liquid, gas, or can be a gas liquid, or two insoluble liquids. So let's give you some real examples regarding to fluid-fluid reaction. Can be a production of a desired product or separation of a constituent from a fluid. For example, like the soap formation. For production of a desired product, for example, like the salt formation, if you have a fatty acid react with NaOH, then you will get this is a soap formation, right? And the other, if you have a chloride, gas for chloride react with a benzene, liquid benzene, then you will get the chlorobenzene production. You will have a chlorobenzene, right? And HCl as a byproduct. So this is a formation of a desired product by using the fluid-to-fluid reaction. And regarding to a separation of a constituent from a fluid, for example, like if you want to remove the carbon dioxide from a liquid mixture, then you can use this equation, right? Because gas carbon dioxide can react with K2CO3 in the liquid. Then you will get this liquid phase, so you have chance to remove the carbon dioxide from this liquid. Okay, so this is also involve the fluid-to-fluid reaction because it involves the gas-liquid reactions. Okay, so before we move to the detailed deviation for fluid-to-fluid chemical reaction, I hope you can have some pictures. So I'm going to use this slide to show you, to demonstrate what we need to consider when we deal with a fluid-to-fluid chemical reaction. So now we have a gas A react with liquid B, then probably we will generate any types of forms or any types phase of product R, and also we assume R can easily get out of the interface, so we don't need to consider the production of R. Okay, so under this case, the left-handed side we have gas A, and right-handed side you have liquid B, and we have interface between gas and liquid. And as we mentioned, it also can be a liquid versus liquid, but both this liquid belongs to insoluble liquid. But here, the picture I draw is a gas A react with liquid B, and we have interface between gas and liquid. Okay, and as we mentioned, as long as you got two different phases, so in between, let's must have a film layer in between. And the left-handed side in the film layer, we call it as a gas film, and right-handed side near the liquid, we call it as a liquid film. But all this part belongs to liquid film. Okay, so left is gas, film, and right-handed side is liquid film. Okay, so what you have is you have the gas A, right? So in order to describe the concentration of the gas, usually we use the partial pressure of reactant A, PA, to describe how much gas we have. Here is PA. So when the molecular A enter the gas film, so the concentration or partial pressure of reactant A is decreased as a function of location, and when it reach the interface between the gas and liquid. And when the gas A going to enter the liquid film, it involves the solubility of the gas in this liquid. So we have the solubility of the gas A in this liquid that will obey the PAI equals Henry's constant times CAI. So you need to check as long as you know the Henry's constant HA, then you know the solubility of CAI here. So now you have CAI here, and also decrease as a function of location because it also obeys the diffusion phenomena diffusion behavior, right? Then when you reach the bulk liquid, then it will keep constant Ca inside the bulk liquid. So this is the idea. So you can find the same pictures in your textbook, the textbook in figure 23.1. Okay, it's similar, right? Just use the other figure too. Okay, so before we go to detailed deviation, you also need to pay attention some assumptions or some parameter you need to additional consider for fluid-fluid reaction. Okay, so we need to consider the mass transport rate, chemical reaction rate. So the mass transport rate, chemical reaction rate, and equilibrium solubility of the gas into the liquid, and also the contact scheme here, contact mode. Because for this case is you put the A here, B here, right? But some for this case is you bubble the gas A into the liquid B. But sometimes probably you just have a bake, you put the liquid here and you just put the gas on the top of it. So this is the contact scheme or contact mode between the gas A and liquid B. So you need to consider all the parameters, all the situations for your experiments. And now then next is some assumptions for this kind of fluid-fluid reactions. We consider the following second order reactions. Is gas A react with liquid B, then we will have product R. And in this case, we assume it is a second order reaction. So the consumption rate of reactant A can equals to KCACB. And here G to liquid, that means the gas A is going to diffuse into the liquid phase. So we use this to express that. And there's three things you need to know except the second order reaction. Is the gas A in liquid B, the solubility relationship will be obey this rule. So you can, as long as we know the Henry's constant, then we know the CAI, the solubility of reactant A, gas A into the liquid phase. And the second thing is the B is not going to enter the gas phase. That means the liquid B is not going to enter the gas phase. What this means? That means because liquid B is not going to enter the gas phase. That means the reaction, chemical reaction, this chemical reaction only happens in it's not going to happen in the gas phase. So all the reaction only happens in liquid. And that can be in the liquid film or liquid main body, or both. So what this means? So I draw the other figures. Gas A react with B. Then as we know, the interface is here, and film layer is here. And you have a partial pressure. When the reactant gas A enter the film layer, then the partial pressure will decrease. And this drop will involve the solubility of reactant gas A into a liquid phase, right? And then the CAI is also decrease within the liquid film layer, then maintain the constant in the bulk liquid. And as we mentioned, the B is not going to into the A phase, gas phase. So all the reaction only can happen either in the film layer or bulk liquid or both. So now we confirm the chemical reaction only happen in the liquid phase. This is very important. This is a fluid-fluid reaction is more complicated than the case we deal with is a fluid-solid reaction. Why? Because for the fluid-solid reaction, we confirm that the reaction only can happen on the surface of the solid, right? But here, things more complicated because the chemical reaction can be happen in the film layer or in the bulk liquid or both. So you need to figure out. And what's the portion? How much reaction? What's the portion of chemical reaction happen in the liquid film and in the bulk liquid? Or you don't know, right? And we need to quantitatively know that. then you can write down the consumption rate of reactant A. So this is the why this fluid-to-fluid reaction is more complicated than the fluid-solid reaction, because the chemical reaction you need to figure out in where and how much reactant A be react with B in liquid film or bulk liquid or in both region. Okay, so in order to move forward, there's some special term we need to emphasize. So to complete the rate equation, so here you know V sub R we call a reaction volume. So in fluid-to-fluid reaction, that will be the sum of the VL is the liquid volume and the gas volume. And VL is a liquid volume, VG is a gas volume, and VR included the total. So if this is the system we deal with, so let's read this volume included the gas and the liquid is we call the reaction volume. Okay, and the S is the gas liquid interfacial area. And the FLO is VL over VR is the liquid reaction volume ratio. FG is a VG VR gas reaction volume ratio. AL is a S interfacial surface over VL is a surface liquid volume ratio. A is a surface reaction volume ratio. So why we need to know that? Because we want to well describe the rate equation by different units. So for fluid-to-fluid reaction, usually people deal with would be the 4 double prong or 4 prong, means the consumption rate of reactant A per reaction volume. Because now we deal with the liquid, right? So usually it is not because the reaction is not only happen on the surface of the solid, not only a specific surface. You need to consider the volume, total volume. So here, usually we deal for fluid-to-fluid reaction, we use the volume per volume to express the consumption rate, to express the rate equation. And minus R, AL is the consumption rate of reactant A per liquid volume. And double prong, because some reaction only happen on the specific region or on the specific area, so consumption rate per interfacial area can be also the other option. So as long as you know these 3 different expressions by different units, then you know consumption of reactant A can be expressed like a 4 prong times VR, AL times VL, double prong times S, right? So when you also can write down 4 prong equals to this divided. You can divide this here. So VL over VR, so FLO times RAL, and S over VR, so S over VR, so it's a RA double prong. So you can easily convert them into different units, and you also know the relationship between 4 prong, RAL, and RA double prong. Okay, so today we just ended here.